Welcome to the world of chemistry. This is our very first set of notes, so let's get started. So first off, the thing you have heard thousands of times in your time at school is about the scientific method. The scientific method is the process that scientists follow. Now, even though these steps are listed in order, scientists don't always necessarily follow them in order, and it's much more of a bunch of circles than a straight line process. But overall, scientists make some sort of observation about something they've noticed. This causes them to ask a question as to why it's like that. Is there a way to fix that? Some sort of question. Then they create a hypothesis about how they could fix that, why that thing works the way it does. Then they're going to design an experiment to answer that question to hopefully support their hypothesis. That experiment will yield some sort of results, and from those results, the scientist will get a conclusion. Now keep in mind, scientists never prove anything. They just get evidence that supports that. They do not prove things directly. That conclusion may cause them to have more questions, or maybe their conclusion didn't support their hypothesis and they think it's because of their method, so they might go straight back to the method step and redesign their experiment. This isn't just a step-by-step process. You can go backwards, fix things all the time. So there are two different types of observation/measurements, or data where you're going to be expected to gather. The first one is we make qualitative observations of reactions. Qualitative, think of the word quality. And these are things like changes in color, the physical state of something. This is a liquid, that is a gas, something we can see with our eyes, a quality that it has. On the other end, we have quantitative measurements, which are always going to be numbers. You can think of quantitative, quantity. In this classroom, and in all science classrooms, we will be using the SI units, which are based on the metric system, not the English system that we use in the United States. So a little chemistry in action story for you. In September 23rd, 1999, we had the Mars Climate Orbiter. It cost $125 million, and it was supposed to go to Mars and orbit, collect all sort of wonderful pictures of information for us. However, it entered Mars' atmosphere about 100 kilometers lower than it was planned. This meant that it got destroyed by the heat, which basically means we burned $125 million. And that's for a few reasons. They were making the assumption that 1 pound was the same as 1 Newton, which I know isn't a unit that you use a lot, but it's not. The problem is that the American scientists were using pounds and the European scientists were using newtons, and no one bothered to check with the other as far as what unit they were using. And since 1 pound actually equals 4.45 newtons, the thing was way heavier than it was supposed to be, which means it entered way lower than it was supposed to. A quote from one of the scientists involved in this project is that this is going to be the cautionary tale that will be embedded into introductions to the metric system in elementary, high school, and college courses till the end of time. And I'm still using it 20 years later, so he's probably correct. So this is why it's important to always pay attention to your units so you don't light $125 million on fire. So when we measure, we are using a measuring tool to compare some dimension of an object to a standard. This is really good because at one time, the standard for length was the king's foot. So this meant if the king was young and was growing, the king's foot size kept changing. Or when the king died and we got a new king, they probably didn't have the exact same size feet, so that meant a foot became a different measurement. This is a big problem because if someone hasn't heard that the king's feet grew, they might be using the wrong measurement. Obviously, that sounds super ridiculous, and it was actually used to be done that way, but it's not anymore. Now we have standards that we use. But because we have those standards, we have developed what are called significant figures. I'm going to say this now. Some of you will not believe me, but significant figures will be used in this class all the way till May. If you choose not to learn them now, you will be losing points on every assignment until the month of May. It's not a good choice, so pay attention. So counting is a common type of measurement. The measurement is exact and therefore can be expressed without error. So for example, if there are 26 students in the classroom, there are truly 26 students in a classroom at that given time. They're not secretly 25 or 27. Counting is an exact measurement. However, anytime we have had to measure something, we have some degree of error or uncertainty. For example, if you were asked to measure the width of your desk, and I handed you a meter stick, but it had absolutely no markings on it, you're not going to be able to measure it at all. Meanwhile, if I gave you a meter stick and that only has centimeter readings, then you're going to have to estimate how many tenths of a centimeter the desk width is. However, if I gave you one that had all the way down to millimeter markings on it, you could estimate to the hundredth. So we can only go one past whatever unit we are given on our measuring device. That last digit is always going to be an estimate. So in science, measurements can only have one degree of uncertainty or one estimated digit. That one digit will always be your estimate. So significant figures are the certain digits and one estimated digit, and the number of significant figures will tell us the exactness of the measurement. Exactness is also called accuracy, or how close the measurement value is to the actual value being measured. So we have 5 rules for significant figures. They are, all digits from 1 to 9 are significant. So anytime you see 1, 2, 3, 4, 5, 6, 7, 8, 9, it is a significant digit. Perfect. Zeros are where things get tricky. So there are 4 different kinds of zeros we have to be concerned with. The first one are the sandwich zeros, the in-between significant digit zeros. So for example, in the number 2007, that has 4 sig figs. That's the abbreviation we use for significant figures, because they're in between, and in between zeros are always significant. So we have a significant 2, a significant 7, and since they are in between, it makes them significant 2. Then we have trailing zeros, which are zeros that are at the end of a number, and they are only significant if there is a decimal point. So for example, 100.0 has 4 significant figures. Those are trailing zeros, but it has a decimal point. All of them are significant. Meanwhile, the number 100 only has 1 sig fig because there is no decimal. Our third type of zeros is zeros that are at the beginning of a number. Since they serve as placeholders, they are never significant. Even if there's a decimal, they are never significant. And you can see that in the number 0.0025, only the 25 is significant because leading zeros are never significant. Zeros following a decimal significant figure are also always significant. So once again, this 0 at the end is significant because that decimal is there. The decimal doesn't have to be at the end. Now, I personally just do best with these rules memorized. I can do significant figures all day long because I just have these rules in my head. And for those of you who are kind of good memorizers, maybe memorizing the rules is the way to go for you. Up to you. However, there is what I call the cheat sheet version of determining if a number is significant or not. And I often call it the Atlantic Pacific way of doing it. So I want you to visualize the United States. So think about the United States in your head. We live on the far right side of the country, on the Atlantic Ocean side. On the other side of the country, on the far left side of our country, if you're thinking about a map, we have the Pacific Ocean. Pacific starts with a P, stands for present. Atlantic starts with an A, stands for absent. So you ask yourself, is the decimal place present, Pacific, or absent, Atlantic? If the decimal point is present, you count from the Pacific side of the number, the left-hand side, West Coast side, however you want to visual it. You go until you find that first non-zero number, and then everything after that becomes significant. Meanwhile, if the decimal point is absent, meaning there isn't one, we go to that Atlantic side, that right-hand side, that East Coast side, and we once again go until we find our first non-zero number, and then once we found it, every number after that becomes significant. So you just have to ask yourself, is the decimal absent or present? And go towards the center of the country from whatever side you start on. So this is the second way of doing it. Memorize the rules, do Atlantic Pacific, doesn't matter to me, but you will be using sig figs until May, so make sure you have them down. For those of you who maybe didn't have the map memorized in your head, here is a nice visual of the United States. Once again, Atlantic over here, Pacific over here. Same rules as were on the previous slide. So let's do a little bit of a learning check. Question 1 asks us which answers contain 3 significant figures. Once again, you can use the rules. Atlantic Pacific, doesn't matter. Let's use Atlantic Pacific on A. So we see that the decimal point is present. So we're going to start on the Pacific Ocean side. I go until I reach my first non-zero number, which is this 4. Then everything after it becomes significant, which means I have 1, 2, 3, 4 significant figures. So it can't be that one. So then I look at B. Let's talk about it in terms of rules this time. So I look, I know that all of my non-zero numbers are significant. So that's 3 right there, looking pretty good. So then I have to think about my rules pertaining to zeros. I don't have any sandwich zeros. I don't have any trailing zeros. I only have those in the front leading zeros. And we said in our rules that leading zeros are never significant. So that means this number only has 3. Ding, 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 we have a winner. But we might have more than one correct answer. That can happen sometimes. So let's see about number C. C, you could do the Atlantic or the Pacific way. Let's do Atlantic Pacific. So in this case, I don't have a decimal point, meaning that it is absent. So I start from the Atlantic Ocean side of our country, and I move until I hit my first non-zero number. So I'm going to go past the 0 here because it's a 0. I go to my first non-zero number, and then everything past that counts. So 1, 2, 3. Meaning that for 1, our correct answers are B and C. Number 2 tells us that all the zeros are significant in which of the following. So we go through. In this one, I instantly see those leading zeros, and we know leading zeros are never significant, so it can't be A. In B, I see that I have those zeros at the end. The zeros at the end were the tricky ones because they were the sometimes. And what made the difference is if there was a decimal point or not. There is a decimal point, which means they are significant. So B answers my question right there. But just like before, we want to double check and see if we have more than one correct answer. Now, when you see a number written like this, a lot of times I get students that freak out. My best advice is to ignore the 10 to the number. Just cross it out in your mind. If you're being asked about significant figures, it doesn't affect you at all. Once again, it only doesn't matter if we're talking about significant figures. So all you're looking at is the 2.050. Doing Atlantic Pacific, I see that the decimal point is present, so I start on the Pacific side. I go to my first non-zero number, and everything after that becomes significant, meaning the whole number is significant. So look at that. B and C are our correct answers again. Now, number 3 is one that can be tricky for students sometimes. So say you enter into your calculator and you get 534,675 is your answer. But Ms. Hingston tells you your number can only have 3 significant figures. So you're always going to start at the beginning of your number, and you're going to count over the number you can have. 1, 2, 3. Then you peek next door and see if that next door number, in this case our 4th number, rounds it up or not. You know your rounding rules. 5 and above, round to the next number. 4 and below, do not round. So this is a 6, meaning that's going to round that 4 to a 5. So I have 5, 3, 5. And some of you are instantly like, hey, that's A. That's a great answer. But let's think about that for a second. If I told you you could have $534,675 or $535, you wouldn't say, well, those are basically the same number, so it doesn't matter to me. You know those are 2 dramatically different numbers. When we round to sig figs, we just replace all those numbers we've essentially cut out with zeros, like answer B. Now some of you might be thinking, what the heck is answer C? Now I can tell you that answer C is a correct answer, and we are going to dive into why coming up. But let's do one last sig fig practice. In which sets do both numbers contain the same number of significant figures? However you get there is up to you, but this number has 3, this number has 4. Can't be the same. This number has 4, this number has 1, that's not the same. And in C, this number has 2, because none of those zeros count. And this number has 2, because none of those zeros count. So that's the same. If you don't know where I was getting these numbers from, make sure to ask for extra help. So now let's state the number of significant figures in each of the following. I want you to pause this video and try these on your own, and then come back and check your answers. So as far as number 5 is concerned, zeros in the front do not count. The 0 in the back does because of that decimal point, so this one has 2. Similarly, since our decimal point is present, we go to our first non-zero number, go over, all of these are significant, making it 4. Once again, leading zeros never are significant, so this only has 1. Trailing zeros are significant as long as there's a decimal point, so this has 3. Now 9 probably got you. The unit on number 9 is B's. How did I figure out how many B's I had? I counted them. Are counts exact numbers or are counts measurements? Counts are exact numbers, meaning I do have 2,080,000 B's. All 7 of those numbers are significant. So always check your unit to make sure you weren't actually counting. But all of these meters, liters, grams were measurements, so we could do significant figures. So this brings us to significant numbers and calculations. In chemistry, you are going to be doing a lot of math. I joke that chemistry is science math. And when you give me an answer, you don't just get to write down everything that your calculator tells you. You have to give me your answer in significant figures or you will lose points. So let's talk about how that works. So a calculated answer cannot be more precise than the measuring tool. A calculated answer must match the least precise measurement. Significant figures are needed for final answers from adding or subtracting problems and multiplying and dividing problems. So let's talk about adding and subtracting first. The answer has the same number of decimal places as the measurement with the fewest number of decimal places. So if your fewest is no decimal places, your answer has to have no decimal places. If your fewest number is 2 decimal places, your answer can only have 2 decimal places. So for example, the number 25.2 is 1 decimal place. If I add it to the number 1.34, that has 2 decimal places. Now if you enter that into your calculator is going to tell you that the answer is 26.54. And some of you would be very happy to write that down. But remember what we said, the answer has the same number of decimal places as the measurement with the fewest decimal places. So if I have 1, I have 2, 1 is the fewest, which means your Miss Hinkson answer is going to be 26.5 because it can only have 1 decimal place, and that 4 doesn't round up my 5. So let's do a quick learning check. I want you, welcome to use your calculator, to round the answers to the correct number of significant figures. So once you've entered these into your calculator, you should have very easily gotten some answers. The thing about this, though, is you had to put your answer in the correct number of significant figures. So for the first one, your calculator told you 256.75. But we can only have 1 decimal place because these two numbers each only had 1 decimal place, making 256.8 our correct answer because the 5 rounds up the 7. Similarly, on the second one, your calculator would have told you 40.725, but we can once again only have 1 decimal place because of our 18.2 here, which makes our correct answer 40.7. Now, more often than not in here, we are going to be doing multiplying and dividing, and different rules apply for multiplying and dividing than did for addition and subtraction. So we are going to round and add zeros when necessary to the calculated answer until you have the same number of significant figures in your answer as the measurement with the fewest number of significant figures. So you essentially look at all the numbers you multiplied or divided together. You find the one that had the fewest number of significant figures in it, and that's the number of significant figures your answer can have. So for example, if we have 15.7 times 0.63, we see that 15.7 has 3 significant figures, 0.63 has 2 significant figures, so our answer can only have 2 significant figures in it. So let's do some practice problems. Get out your calculator and practice these with me so you can make sure you know how to get these in your calculator. So if you multiply 2.19 times 4.2 into your calculator, it is going to tell you that the answer is 9.198. But you're smarter than that because you learned that when we multiply or divide, our answer can only have the same number of significant figures as the number with the lowest number of significant figures. So if we have 3 and we have 2, our answer can only have 2, making 9.2 our correct answer. Similarly, in question 2, if you multiply 4.311 and divide it by 0.07, your calculator is going to give you a big long number out, but you know that we have to look at significant figures. This has 4, but this buddy right here only has 1 significant figure. So despite the fact that our calculator gave us this monster of a number, we have to round it to 60 because we can only have 1 significant figure. We peek next door. The 1 does not round up our 6, so we can just make it 60. Note we do not put that decimal point with all of the zeros because those would all be significant. Now, number 3 may have got you a little bit. You have to remember your order of operations from math. And if you remember order of operations, you have to do multiplication before you did division. If you entered it correctly into your calculator, you got this nice number out of it. However, when you looked over your numbers, you saw that 2 of them only had 2 significant figures in it, which means the only answer you would have needed to give Ms. Hinkson to get full credit is a nice 11. Significant figures really aren't that bad. The sooner you learn them, the better off you are going to be. So learn them now. Which brings us to our other thing we need to talk about, which is scientific notation. Scientific notation is a way of expressing really, really big numbers or really, really small numbers in an easier way. So they are best used for very large and very small numbers because it is a more concise way of writing it out. Basically, you get to skip writing a whole bunch of zeros, which is good. So how scientific notation will look is it will always have a number between 1 and 10. 2.5, 7.8, it will have a number. And then it will have a power of 10. So n, being our number from up here, times 10 to the a certain number. Keep in mind, when you divide by a number that is in scientific notation, you are going to want to use parentheses on your calculator to save yourself the headache. So to change from standard form to scientific notation, we're going to place the decimal point so that there is one non-zero number to the left of the decimal point. We're going to count the number of decimal places that decimal point has moved from the original number, because keep in mind, all numbers have an imaginary decimal point at the very end of them. However many places we moved that decimal point will be the exponent on the 10. If the original number was less than 1, then that exponent is going to be negative. So when you have a really, really small number, your exponent is negative. If the original number was greater than 1, then the exponent is going to be positive. So really, really big numbers have positive exponents. So let's look at some examples. So if you were given the number 289,800,000, we are going to use 2.898 because we can't get rid of non-zero numbers. Now remember, there would have been an imaginary zero right here, and we moved it 1, 2, 3, 4, 5, 6, 7, 8 places, which makes our number 2.898 times 10 to the 8th. On the other end, if we had 0.000567, I'm going to move that decimal point till I only have one zero number in front of it. 1, 2, 3, 4. So I'm going to have 5.67, and I moved it 4 places. But since I moved it 4 places to the right, or I just remember when I start with a really small number, you use a negative exponent. So in this case, we have 5.67 times 10 to the negative 4th. Now, if we're going in the opposite direction, where I've already given you a scientific notation number, and you're trying to make it a standard number, you simply move the decimal point to the right if it's a positive exponent, and you move the decimal point to the left if it's a negative exponent. Once again, always remember, positive exponents mean you're trying to make a really big number, and negative exponents mean you have a really small number. So if you had a negative exponent and then you have a really big number when you're done, you moved it in the wrong direction. And then once again, if our number was bigger than we had things for, you add zeros to fill it in. So if you were given 5.093 times 10 to the 6th, positive exponent, going to move to the right. So we move 1, 2, 3. Then we run out of spaces. I need to move 3 more. So I'm going to add zeros in its place to make 5,930,000 or 93,000. On the other end, if I was given the number 1.976 times 10 to the negative 4th, since that's a negative exponent, I'm going to move to the left. I move the 1, then I run out of space, so I'm going to add 3 zeros to fill it in, making my number 0.001976. See, scientific notation isn't that bad. So let's do a quick learning check. I want you to express these numbers in scientific notation. I want you to try these on your own. We've done some practice. I have faith you can make it happen. And come back once you have your numbers ready. Your correct answer for these are as followed. Check your answers and come back with any questions. Now, the last thing I want to talk about is you can be asked to use scientific notation in math problems. So, for example, I could ask you, what is 2.898 times 10 to the 8th times 5.67 times 10 to the negative 4th? We have to combine sig figs and scientific notation in here. When you enter it in your calculator, it's going to give you this big number, but we should be able to round it to 1.64 times 10 to the 5th. Now, some of you are wondering, what if I didn't put my answer in scientific notation, Miss Hinkson? Now, if I told you if I didn't say you had to, you could have made it 164,000, and I would have still given you credit. But if I said answers must be in scientific notation, you have to put it in scientific notation. Similarly, we could have divided those numbers by each other. Still can only have 3 sig figs in our answer, making it 5.11 times 10 to the 11th. Now you can see in the second case, not writing it in scientific notation means that you would have had to write out 9 zeros. Chances are you will have miscounted, and then you would have gotten it wrong, so scientific notation can really be your friend. Now, some of you may be thinking, I didn't get even close to those answers in my calculator, Miss Hinkson. You probably entered them wrong. So please make sure to come see me so we can talk about how to enter scientific notation into your calculator. Thanks for watching this video.